I am Illuscri, and this is From Nothing to Us. Book 1, From Nothing to Lucy, Chapter 2, The Birth of Stars. This chapter takes place everywhere and lasts from 375,000 to 260 million years into the story of the universe. I must start with a warning. You'll be waiting for far longer than last time. Thousands of years will quickly melt into millions, and I fear events will move slowly for a great many chapters. That's not to say this will be boring, just that each episode will cover large spans of time. So you should look to invest in several very long books while the years go by. That's not to say this will be boring, just that each chapter will cover large spans of time. So, you should look to invest in several very long books while the years go by. But first, I shall go back in time to when the first atoms were being formed. In researching the first molecules, I realized there's something there I missed. So, back to the universal forge we go, to the moment when the temperature dipped below that 3,000 Kelvin threshold. We're back to that era of furious activity, so you'll have to look very closely. If you do this, you'll notice that helium is the first full element to form, not hydrogen. This head start is not put to waste by the newborn atom, and it immediately goes to work forging the first molecules in the universe. It's difficult to say which was first, but two molecules are formed, both simple. A helium atom combined with a proton, called helium hydride, and two helium atoms, molecular helium. Both are ions, basically meaning they're electrically charged. We don't know which was the first molecule, but only one survives into the future, helium hydride. The other is broken apart by the photons that have just been allowed to fly free. A short and unfortunate life that must be. Hydrogen is the next atom to form, and it's quick in finding other hydrogen atoms to hold tight to, forming molecular hydrogen. Each pair of atoms is without charge, the first molecule to boast such a feat. From here, lithium is born, along with a small soup of molecules. And don't worry, I'll only describe the most important ones remaining. Those are hydrogen deuteride and lithium hydride. All you need to know about them right now is that they may prove themselves important in the future. Keep an eye on them, as well as molecular hydrogen. Before we head on with the narrative, I have to dip into the realm of speculation. There's a small chance that some higher elements have been born along with the others. That's oxygen, carbon, nitrogen, potentially up to iron. Now, if any of these have been made, they're in extremely small amounts, but keep their possibility in mind. For now, we re-enter deep time. Through the churn of millions of years, that red glow fades fully into the infrared, and to your eyes, the universe is blacker than night. No stars to fill the sky, and yet, if not for your suit, the temperature alone would kill you for some time. Despite the uniformity and seeming nothingness, there's motion. The gas all around you flows in grand rivers through space. I imagine them twisting and twirling around each other, though I admittedly have no evidence for this. What may be known, though, is that these flows are very fast, up to 30 kilometers per second, relative to the reservoirs of dark matter looming in the background. The gravity of those silent behemoths is slowly pulling these rivers into themselves. That's not to say dark matter, if it even does exist, is static. Some of it may be very fast in its own right, though before I can say anything more conclusive, we have to, find the stuff first, unfortunately. You have time to ponder it, though, for the span from the birth of the first atoms to our next stop in the tour is larger than anything you've gone through so far. In fact, most all of the time periods for a good while will be very long. So from now on, I won't bother going through this whole farce every time a few million years goes by. Anyways, welcome to around 10 million years after the beginning of time. Look at the temperature. The background radiation of the universe has cooled enough for liquid water to exist practically anywhere. Now, this may have huge consequences, or it may mean nothing. It all depends on whether or not water is a thing that exists at all. One of the major ingredients for water is oxygen, and if that was not made earlier, then we're out of luck. But if it was, well, think of the possibilities. If oxygen's around, then carbon is too. And when carbon and water are in the same place, wonderful things can happen. You are a perfect example of that. There's a solid period of 7 million years where these conditions are possible. With a whole universe to work with, who knows what sort of life might be born in this time? Now, let's take our heads out of the nebulae. It took billions of years for life on Earth to become multicellular, and with far different initial conditions than just a pile of water floating through space. So, a few million years probably won't do much even if water is around. And the universe only gets colder as time goes on. There's no stars and planets yet. Any life that's born now will freeze soon enough. On that cheery note, let's accelerate time until just before the 100 million year mark. Gas spirals into the hearts of dark matter halos. Large structure takes shape over grand time, though at this time it's little more than giant clouds separating from each other and condensing. Zooming into these clouds, we find turbulence as material flows and collects. Much of these clumps are too warm to let gravity do its patient work any further, but some areas are cooler. Both of hydrogen's atomic and molecular variants let go of their heat over time in the form of radiation, but only to around 200 Kelvin, too hot to collapse any further. The magic ingredients that cool clouds further, down to a much more manageable 128 Kelvin, are our friends helium deuteride and lithium hydride from earlier. Without them, star formation may have taken a good bit longer. Gravity is happier wherever all this cooling happens more. Cold matter is more pliable than its hot-headed counterpart. Gas clouds condense quicker, and as they do, they fragment into smaller and more turbulent clumps until we get to the scale of the modern solar system. The more mass in one area, the faster and more violently it collapses. At a certain point, it stops clumping to the dark matter around it, and instead latches onto its own gravity and clumps around itself. At the center of every one of these massive fragments is a growing sphere of gas that's steadily heating up as more material crunches down onto it. Around the ball, a rotating disk forms made of the gas that's spiraling inwards. If there are charged ions in this disk flowing in the right way, huge magnetic fields may be born, casting jets of material off into space. The sphere in the middle crunches any loose hydrogen into its molecular pairs until no atom is left alone. But the temperature has been steadily rising with pressure, and once it gets above 2000 Kelvin, those pairs are shaken apart again. Cruel of the budding protostar to do that. Protostar. Well, as material has accumulated, that central mass has begun to glow. Slow at first, but growing with more mass. Not nearly as brightly as a true star, mind you, and it still has some patience to spend before full ignition. But I don't want to lessen what's been done here. This is potentially the first light produced in the universe since the birth of that cosmic background. No longer are you alone in this place. There are precious few at first, but As time turns, you should be able to see burgeoning protostars burning red constellations into the black of the night which had seemed so eternal. Those points only grow brighter and more numerous as the years churn. Many of these protostars are or will be around 20 to 40 solar masses, though the one we have visited, the first in the universe, I suspect is closer to a far rarer 150 solar masses, if not larger. The reason I guess at this, and not the far more common 20 to 40 solar mass stars of this time, is because of how much faster it is to produce a larger star than a smaller one. At such sizes, any protostar over 20 solar masses gluts on the gas around it and produces a disk of such bloat and turbulence that huge sections of material are cast away. Other, smaller protostars are born from these sections relatively quickly, in only a span of several centuries. What's being born is a tight solar cluster, much more cluttered than the one in which Earth is in now. If the parent protostar were where the Sun is now, its children would lie well within the bounds of the solar system. Eventually, the parent starts to fuse the deuterium lying in its core, the first fusion since the dawn of time. It burns ever brighter through thousands of years. Its lighter children grow notably slower, just as they will grow up to become much longer-lived stars. But let's turn our attention to that first, impossibly massive protostar. Internal pressures have grown to the point that hydrogen can no longer support its own weight, and it follows in deuterium's footsteps. The core fully ignites in a fury fueled by fusion, and an adult star is born. Less than 10,000 years have passed since it first became a protostar. That's no more than a twitch compared to the timescale of much smaller star births. But let's take a look at what's been born. A star of 150 solar masses would look bloated and angry when put next to our sun. The temperature at the surface reaches 100,000 Kelvin, granting it a light blue shine brighter than 1,000,000 suns. At around 4 times the radius of the sun, it's actually smaller than modern supergiants of much less mass, which I found interesting. Don't really know why that is, but it's interesting. At the start of its life, it very likely has no metals. It is vast majority hydrogen and helium, with only the tiniest bits of lithium, unlike modern stars like the sun, which have traces of oxygen, carbon, nitrogen, and many other higher elements. Don't expect this to be the case forever, though. For now, let's look at the space around the star. Only 10,000 years after hydrogen ignition, the disk around it has been heated to the point that it expanded and broke apart. The gas cloud that has been fueling the disk no longer sends more material in. The star is well and truly on its own now. The light it sends out not only heats atoms, but also strips them of their electrons, a process called ionization. The universe used to be completely ionized in the time before atoms were born, and the birth of stars starts the long process of converting the universe back to such a state. Each of the very first atoms has an expanding bubble of ionizing gas around it. Back to the first star. Hydrogen fusion produces helium, which is the dominating process in the star's core for the majority of its life. After only a few million years, helium starts to fuse into carbon, with lighter elements produced in the background. This lasts much shorter, on the scale of thousands of years, and it only gets shorter from here. Carbon fuses into neon, neon to oxygen, and oxygen to silicon. We're now at the grand end of the star's life, when it has bloated to many more times the sun's radius. Unlike other massive stars, this one is too huge to immediately start fusing its silicon. Because of some strangeness with photons being absorbed in the core, there's suddenly not enough energy to support the star against its own gravity, and it starts to violently contract. Pressure spikes as the core is pressed by the weight of a falling star. Silicon is forced together so fast that the iron it produces is accompanied by a burst of angry energy far exceeding gravity. The core explodes outwards with such ferocity that it drags the rest of the star with it. Huge amounts of heavier elements are forged in the rout, from nickel to gold to radium to uranium. Such conditions have not been seen since the first moments of the universe. At the end of it, the destruction is complete. The first star is dead. Unlike smaller supernovae, the only remnant left behind is the rapidly expanding cloud of gas and newly forged metals. Neutrinos beyond measure were expelled in the blast. But despite it all, a wonderful zoo of elements has been reaped from the destruction. All the elements we're familiar with on Earth now exist, albeit in this single isolated region. And the multicolored display left behind is sure to dazzle anyone watching from a safe distance. Stars of similar or even larger size follow suit in the following millennia, and slowly, small packets of the universe are populated with heavier elements. But do not doubt those smaller stars either. I say smaller, but the vast majority of them are far more massive than the Sun, being in that 20 to 40 solar mass range I mentioned earlier. These stars burn healthily for the first few million years, before teetering to the end of their life with the burning of silicon into iron. Here we see much more typical supernovae. Silicon fusion in these stars only takes a day, and once that fuel is spent, we're left with an iron core. Iron has an extraordinarily stable nucleus, and so it takes much convincing for it to fuse. The conditions in the core of the star right now are not nearly extreme enough to be convincing, and so the iron core undergoes catastrophic gravitational collapse. The outer layers of the star rebound off the core in a less energetic explosion as in the first star, though it's still furious enough to produce higher elements. The core, though, doesn't follow suit. It keeps going. For stars from 10 to 25 solar masses, the core contracts so violently and so completely that protons and electrons fuse into neutrons. All atoms are destroyed, and only a glowing, ultra-dense soup of neutrons remains. A teaspoon of such material would weigh over 40 times the amount of gold humanity has ever mined. The fact that an object with those conditions is even possible sparks awe. An object called a neutron star. But for stars above 25 solar masses, the core hands its destiny to gravity. Down it spirals. The atoms try to push against it, but their struggle is in vain. Pressures mount and light itself slugs through the gravity until a certain density is crossed. The core fades to black. Its story essentially ended. A black hole has been born, though it may not be the first. If a star is massive enough, its death will manifest as the whole star collapsing at once into a black hole. No explosion, not even a whimper. The bigger the star, the shorter its life, so I suspect the first black hole was formed from some sort of oversized star. For extremely massive, extremely rare, only theorized stars of 100,000 solar masses, such black holes could serve as the seed for much scarier objects, supermassive black holes. These monsters will form over the next couple 100 million years or so, but regular black holes from your typical massive star don't explain just how monstrous supermassive black holes are. There simply isn't enough time for them to form. Thus, it's believed a kind of something was being formed early enough in the universe to act as the seeds. 100,000 solar mass stars are one of those possibilities. Another is a strange sort of object. In the gas clouds that formed the first stars, some may have had much, much larger regions collapse in on themselves. Such events would have produced hugely overmassive proto-star-like things that never reached the status of star, and instead turned directly into a monstrous black hole thousands of solar masses. What's extraordinary to me is that all the creation I've told you about so far in this chapter took place around the same time. It's believed this was at the 100 million year mark, but it could have easily been as late as 200 million years, we just don't know for sure. And now that I've explained star birth, life, and death, I can accelerate time once more and watch the grander flow of the universe. Going forward to the 200 million year mark, it's likely stars have begun to form en masse throughout space. Though I don't think there are planets yet to view the night, the sky must be swimming with colors and stars and clouds of gas and dust. Dust is a relative newcomer on the cosmic stage, since it's made of those heavier elements formed in supernovae. Before the first stars, all was gas. Allow me to backtrack to planets for a moment. When I was researching this chapter, I thought gas giant planets might have formed around the first stars, but there seems to be little evidence for this as far as I found. Surprisingly, gas giants seem to require heavier elements to form, even if most of their mass is hydrogen and helium. This is because huge metal cores must form first for the gas to accumulate around. Otherwise, it all just gets dumped into the star instead. So it's possible that planets began to form around the second generation of stars that have begun to form by the 200 million year mark. These systems would have had some heavier elements from the first supernovae, so I don't see why it wouldn't be possible. But as ever with this period of the universe's history, all is terribly uncertain. Let's move on. Since the first metal-free stars burned so quickly, most of the star-forming fuel in the universe is mixed with metals by around the 260 million year mark. These clouds have much more ways to cool themselves than just hydrogen, thus cooling far faster than before. As they contract faster, they break apart more easily, and so the stars that form have masses much more similar to today, most being smaller than the Sun. They burn far longer than the first generation, and so many, if not most, of these stars have survived to today, ancient relics of the dawn of the universe, just waiting to be discovered. Some have already been discovered. As this all happens, the reionization of gas across space continues its slow course, still in isolated pockets. And the largest clumps of dark matter, thousands of light years across, continue to attract our flavor of matter. Grand structure begins to form with stars as the atoms. The slow process we see before us is the first hint of the first galaxies. But I shall keep that for the next chapter. Until then. And we've made it to the outro. Welcome to the part of the show where I read and respond to questions and comments you may have for me or the podcast. Since I'm in the very beginning of this journey, there are no comments yet, but if you have any questions, feel free to comment them on whatever program you're using to view this. I know Spotify and YouTube have comment systems, or you can email me directly at illuscri@gmail.com. Also, I forgot to say this, thank you for listening this far. I know it's been probably around 25 to 30 minutes, so thank you a lot. And now I'm introducing a new section to this show, the Corner for Cool Creations. I like supporting other people in their endeavors, so whenever I discover a podcast, see some art, read a book, etc. that I enjoy, I'm going to share it here. I'll try to keep them related to history or whatever topic I'm sharing that week, but no promises. For this week, I must start with the podcast that inspired this one, The History of the World by Chris Hasler. I already mentioned it in the preface, but that was only a mention. I've been listening to this for the past couple months. It's a pretty in-depth history of humanity from, primates millions of years ago, and goes through the grand sweeps of history to today. So, pretty similar to this podcast, except it starts later and has a different style of presentation. I've been listening to this for the past couple months, and though I'm only on the Ancient World volume, Hasler does a thorough job with good presentation. So, a pretty big thumbs up from me. I recommend it for any viewer, even if we inevitably cover the same topics. I think it's valuable to have different perspectives on the same thing, so please don't just watch my podcast. You can find this show on Spotify, Apple, Amazon, iHeartRadio, and a YouTube channel of the same name, From Nothing to Us. There's a page for this chapter on my website, illuscri.neocities.org, and you can find that link in the description of this chapter. I also have a fantasy world-building website at reliul.neocities.org. That's Reliul spelled Reliul, and a world-building YouTube channel that's just called Illuscri. And that is all that I have for today. Once more, thank you for listening, and if you enjoyed the show, then make sure to rate it however honestly you wish, and follow or subscribe, like, all that sort of stuff. I will see you in the next chapter, and as always, go absorb the world some today.